most powerful electrical storm on record detected. The total charge in a single thundercloud could have powered New York City for half an hour. As clouds gathered over the city of Philadelphia in 1752, Benjamin Franklin stood outside with a simple kite-borne experiment and proved the electric nature of lightning. Now, more than 250 years later, scientists have uncovered a shocking secret about the awesome power of thunderstorms. With the help of charged particles originating from space, a team in India has for the first time accurately measured the electric properties of a giant thundercloud, determining that the behemoth contained 10 times more energy than any previously investigated storm. Along with discovering a novel connection between cosmic and terrestrial events, the findings might help solve a 25-year-old mystery in high-energy physics. At any moment, about 2,000 thunderstorms are occurring worldwide. Learn how thunderstorms form, what causes lightning and thunder, and how these violent phenomena help balance the planet's energy and electricity. Since 2001, physicists in Udagamandalem, India, have been using the Gamma-ray astronomy paired energies Phase 3, or GRAPES 3, telescope to monitor subatomic particles called muons. Cascades of these naturally occurring particles rain down on Earth when cosmic rays from the distant universe hit our upper atmosphere. Here's how scientists recently used muons to discover a previously unknown void inside the Great Pyramid of Giza. Intriguingly, the highly sensitive GRAPES 3 instrument often detected slight decreases in the muon shower's intensity between April and June, and again between September and November, just when the subtropical region receives its highest rainfall. This was more of an amusing episode for us than anything serious, says study co-author Sunil Gupta, a high-energy physicist at the Tata Institute of Fundamental Research in Mumbai, India, whose team described their work last month in Physical Review Letters. We were studying high-energy cosmic rays in interplanetary space, and not so much the thunderstorms. Packing a punch. Muons carry negative charge, meaning their paths are distorted by electric fields. Gupta wondered if that property could be used to calculate how much energy the thunderclouds contained. Back in 1929, Nobel Prize-winning physicist Charles Thomson Rees-Wilson measured the electric field inside a thundercloud and found it to be a surprisingly large 12,700 volts per inch. This implied that the storms, which can stretch for miles, should have enormous total electric potentials of around a gigavolt, or the equivalent of nearly a billion AA batteries. But measuring voltage across an object usually requires placing two wires at either end, and nobody had figured out how to do that for a large and amorphous thing like a cloud. Airplane and balloon experiments, which have flown through thunderstorms taking readings at various locations, found electric potentials of tens of millions of volts, with the largest previously recorded event having 130 million volts. Study co-author Balakrishnan Hariharan devised a model that determined how powerful an electric field would need to be to alter the number of muons detected in GRAPES 3. Working backward, the team could then use their muon observations to estimate the electric field inside the clouds above the experiment. In the GRAPES 3 data, the researchers saw the electrical effects of 184 thunderstorms over the course of 3 years. The muons indicated that one particular leviathan, which appeared on December 1, 2014, briefly contained an electric potential of nearly 1.8 gigavolts. That's enough energy to run all of New York City for half an hour, Gupta says. To achieve such high voltages on the ground is almost impossible, he adds. But nature seems to know how to do it almost effortlessly. Dangerous discharge. Because the muon-based measurements can see large areas of the clouds, they are more accurate than plane or balloon-borne experiments. That means prior data likely delivered underestimates, and many thunderstorms should have billions of volts of energy inside them. This, in turn, might illuminate the origins of a long-standing head-scratcher in atmospheric physics. In 1994, NASA's Compton Gamma Ray Observatory, which was built to monitor powerful flashes of light occurring in distant galaxies called gamma ray bursts, noticed a few high-energy eruptions coming from Earth's atmosphere. Nobody has since been able to give a full explanation for why our planet should produce events similar to some of the most powerful phenomena in the cosmos. Though lightning had been suspected to play a role, the thundercloud energies observed in previous experiments were not great enough to explain the terrestrial gamma-ray flashes. Find out how thunderstorms can shoot antimatter into space. Now, GRAPE's 3S gigavolt measurements are the first to suggest that such storms contain enough power to produce this enigmatic effect. Gupta says the team would like to include a gamma-ray detector in their instruments in future to help solidify the connection. They would also like to study how quickly the voltage in a thunderstorm is dissipated through lightning strikes. We want to look for the discharge, he says, because that's what causes most of the damage. For now, the existing measurements have already impressed other researchers. It's an application that nobody has thought of before, says Michael Cherry, who studies high-energy cosmic rays and gamma rays at Louisiana State University in Baton Rouge and was not involved in the recent work. Most researchers in the community would have previously been skeptical that ultra-powerful cosmic rays could be affected by comparatively mundane lightning, he adds. But the results suggest that lightning is one of the most powerful natural particle accelerators that Earth-bound physicists can access. These high-energy processes don't have to be studied in an exotic source like a distant black hole or supernova, Cherry says. We can study them by looking up close and personal at nearby lightning.